Okay, let's, I guess, get started. First of all, are there any questions about? First of all, any questions about homework or policy or anything we're talking about in here? I've heard from one student that they're still looking for a partner. Undoubtedly, there are more of you. Okay, is there anybody still looking for a partner? Okay, I see one. I see two, I see 3 hands, 4 hands. Stand up if you're looking for a partner and make eye contact. Okay? Some people may be very far from somebody else standing up who they can't see. Okay? But make eye contact and that be your partner. If this doesn't work, you can send me email. Okay? But I recommend that should do it. Any other questions about partners or homeworks or anything like that? Okay, any other questions about the class? I heard from Bears, get it in and get it out. Go. No. Okay. Let's get started. No. Okay, so let's get started now. First question is, so any questions, let's say, about anything we talked about? Last class we started talking about data structures. Any questions or comments at that point? Okay, what's important to me is this problem of the day is, to me, very important in understanding data structures. I want to make sure people get it, okay, before we move on. It has to do, we started talking about dictionaries. And what is a dictionary? Okay, it is a data structure that supports the following, I believe it is 6 operations, okay? And we're going to look at, for the next couple classes, we're going to look at different implementations of data structures that realize all these dictionary operations. And in order to do it, we need to make sure we know what a dictionary is. So the operations that we have are, first, we can search according to a key. Okay, see that K? K stands for key. I am giving you a dictionary stores records in a old-fashioned paper dictionary. You had the key was the word. There was baggage associated with or other data associated with the word, like how you pronounce it and what the definition was. Together that makes a record, okay? But the search capability is all done on the key. Search means we are given a key, meaning the string. Let's say if it was used to represent words in a dictionary and a data structure, a pointer to the data structure, and the question is, find me a pointer to the object, to the element, to the record, such that the key is the same. Any questions? Insert says we are given a pointer to a node, okay, a record containing the whole record that is outside the data structure, and we need to put it in the data structure. Does everybody get that idea? That will take a certain amount of time, okay? Delete says we are given a pointer to an element in the record, okay, and we want to remove it, okay? The key thing here is to note we are given a pointer to the element we want to delete, not the key, okay? Notice that's an X and not a K. What is the advantage of defining the delete operation in terms of the pointer to the element rather than the key of the record being deleted? Yes?
It means that you don't have to look up what element the key corresponds to.
If you have it, okay, you don't have to look it up. If you don't have it, you got to look it up anyway, right? It separates the cost of actually doing the manipulation with the cost of finding it. Any questions? What were the other operations here? Clear ink, ka-chunk. We were given min and max, which told us, whenever we have a dictionary on things, in here we're sort of assuming the elements can be sorted, okay? They have, They are people, so they exist in alphabetical order. They are social security numbers, so they go from biggest to smallest. We are not sorting things that we can't put into a linear order. We're not storing them. So if that's true, then the following operations are defined on any world where there is a total order on the objects. There is a minimum element, and there is a maximum element. There is also, for any given element, if you've got a pointer to the element in the data structure, there is a predecessor and a successor. Okay? Meaning, the elements next in logical order, not in the order in the data structure. Does everybody agree we're defining these things at a high abstract level so we can program them? If you want to say who is next after Skeena, okay, it doesn't matter one of you being close. It's that there's somebody out there who's named Skeena Man or something like that that's right after me in alphabetical order. Okay? That would be my successor. Okay? My predecessor would be Skeen. Okay? Or whoever else in the class is before me in sorted order. Any questions about that? Okay? So this is about logical order and not physical order. Any questions about that? Okay? Any questions about what these operations are? If not, let's start to look at some dictionary implementations. Okay? And in particular, the problem of the day is I want to look at 4 different implementations of dictionaries. Okay? We're going to use as our list, as our data structure, a linked list. Okay? We are going to alternate the choice of is it singly linked or doubly linked? And we're going to alternate whether it is sorted or unsorted. That together gives us 4 different flavors of dictionary implementations. And for each one of these, we want to look at what is the worst case complexity of these operations. Okay? Any questions about that? Let's go and think about it. Okay? So let's try to derive these things from scratch and see if we come up with a problem. If I am given a linked list on n items, okay, and I want to search for a particular key, how much time will it take to find the key in the worst case? N. It might be that if I start searching at the beginning of the list, it might be at the end. Does everybody agree? That is a big O of n. Okay? How much time does it take to insert an item into the linked list? Let's say I have a new record. I want to add somebody else to this class. How much time should it take to do that? Okay? Yeah? Say 1. Well, to a certain extent, the answer is right, but how are you going to do it? In order to say it's going to take constant time, implicitly in your head, there's got to be a code fragment that is doing it. Right? How are you going to insert it in constant time into the dictionary? Yes? Keep track of what? So one possibility is, in the code that is in her head, is I am given a pointer to the head, and I am given a pointer to the tail, right? And if you want to insert somebody new into the linked list, what are you going to do? Find tail points to dot next is going to be equal to x, right? X is going to be equal, tail is going to be equal to tail points to dot next. I have to adjust both those things. That's moving 2 pointers. That would be constant time. Does everybody agree with that? What if I didn't want to maintain a tail pointer? How would I do it? Yeah? I could create a new head, or think about creating a new head is scary, but inserting the element at the front of the list, which is what I think you're saying, it sounds right to me, right? What does it mean to insert this new element in? Well, its next pointer goes there. Then the head pointer points to the new guy instead of the old one. Does everybody agree with that? Both take constant time. Both I can do. Either of them is fine. I can do this in constant time. Any questions? Now, let's look at the next operation, delete. I am given a pointer to the element to delete. Okay, let's say this is the element I want to delete. That's x. How much time does it take to delete X from this list? Okay. I hear constant. Okay. How would you do it in constant time?
Well, since you have the pointer to the element, just remove it.
I have the pointer to the element, but actually I'm in trouble. I don't want the pointer to the element. This is a singly linked list, right? I need to make this guy point to that guy. Does everybody agree with that? It's like we're in a conga line, okay, and I'm reaching on the shoulders of the person in front of me, but I need to get to behind me, right? Can't do it, okay? How do I get this pointer that I need? Given a pointer to X, how do I do it? Yeah?
Find the predecessor of it.
You say find the predecessor of it. You want to use this operation. And the answer is no, because this is an unsorted list, right? Predecessor and successor are logical operations, right? So I don't have any reason to believe the one that's holding my shoulders in the conga line is right before me in alphabetical order. Does everybody agree with that? So how do I find that pointer? Yes? I go to the beginning of the list and I have to go bop, bop, bop until I find somebody whose next pointer is X. Does everybody agree with that? Once I have that, then it's a question of simply rerouting the next pointer of this guy to x.next, right? So previous dot next is going to be x.next, and that's going to splice this guy out of the list, right? It's going to get rid of that thing there. Okay? So how much time does it take to delete X from there? Order N. The dominant time is the time to search for that pointer, the guy who's on my shoulders. Right? Order N. Okay? Yes?
How come you couldn't just take the data from the head and copy it into the element you want to delete and then just increment the head?
Okay, so what you're trying to say is you're now suggesting an interesting strategy that might be different than mine. You are saying, I am given a pointer to X. I want to delete the value that is here. Okay? You're saying, why don't I take the data fields from here,
No, head.
from the head, okay? Let's say you want to take the data fields from the head, copy from the head over to write over the values here, right? And then move that pointer up. Does everybody see what he's doing now? Now this seems to me to be an interesting idea. Assuming that each record has a constant amount of stuff associated with it, a constant number of fields, I claim this is an order 1 solution. Does everybody see it? It's not the way I like to think about it or do it, okay? But actually it seems like a perfectly reasonable way to do it. How many people see what he's done? Okay? He's saying, I can't get my hand. Still, he isn't getting his the hands of the guy that are on me. He's saying he knows how to get to the head. He can take the data fields from here and write that over, okay? And then bop the head to head.next, right? And I see no good reason why that doesn't work. If you want to implement it like that, that is a perfectly valid way to do it. And if you want to do that, that is a perfect way to do it. I'll even honor you by making that a constant time thing now. Okay? Any questions about it? Now I could quibble a little bit about, well, what if the record is so big and there's so much stuff in the record that the act of copying it is expensive? But I'm quibbling. Okay, there. I think I like this way of doing it. Yes?
I'm not sure I understand how this algorithm deals with the case where there are several elements in between the head and the...
So what's he going to do? Okay, what's he going to do? Let's take a look at this. He has got a list like this. He has got X. This is the guy that's going, is this one. Right? This is the head. The head, let's say, was Skeena. The one who's being deleted, let's say, is Romney. Okay? What is he going to do? he is going to overwrite the key name of Romney with Skeena. He's not actually I erased it. Look at that. Okay? And now he's going to write Skeena in here, right, where Romney was. He is now going to have head point to the next, what head points to dot next. He's now going to free up this node. Okay? So this node doesn't exist. And nobody else in the tree is in the list is offended by this. Okay, does everybody agree this is working because it is singly linked and unsorted? Yes.
If you search for, let's say, Romney, and now you have a pointer to that node, and then you go and you try to delete it, it's still going to end up being there now.
Okay, so your concern is that if I have a pointer to Romney, and then you delete it, okay, what's going to happen with your old pointer? It's sort of like this. You had Mitt Romney's phone number, but Mitt Romney has had a change in life now. He bought himself a new cell phone and didn't give you his new number. What happens when you call Mitt Romney's cell phone number? It's no longer somebody's going to reassign the number. It's going to point to somebody else, okay? So that the fact that there is that the node's address has changed, you have to internally, if you're doing this in an application, okay, you've got to recognize when somebody's gone away and when a pointer is stale. Okay, that's, I guess, a problem of a stale pointer, right? If this concerns you, notice that if you had Mitt Romney's phone number and you deleted Mitt Romney in any other way, the same problem still exists. Okay, so that isn't really any different in this case. Any questions about that? Okay, does everybody see how? Yes, question.
Does it take constant time to delete
It takes constant time to delete it. We're assuming that each record consists of a key field, a next field, maybe a constant number of extra baggage fields. Maybe their social security number, their address, how many votes they got for president, a small number of things. Okay? So each record is going to be constant space. To delete the record would take constant time, right? I mean, to actually do anything with that memory takes constant time, okay? And if does that answer your question? It may not, so ask again.
I mean that if we want to find X, then we should take O(n) times.
If we want to find the pointer to the record we're deleting, yes, but notice that delete here comes with X as its argument. We are given a pointer to it in the data structure. Okay? So we don't have to find it. Okay? If you're just given Romney's name, you have to find it. Right? But if we're given the pointer, we can blow it away efficiently. Any questions about it? Okay? Good. What about the successor? How do I find the successor to Romney? Okay, if I want to think of it that way. He's not going to have a successor because he lost the election. But in logical sense, where is the successor going to be? Okay, how would I find, given a pointer to a node, maybe I'll clear the ink. Okay, I'm reluctant to do that. Maybe I'll experiment with the eraser. No, that won't work either. Okay? How would I go about doing this? Okay, how would I go about finding the successor, the key after what X is pointing to in logical order? How would I do it? Before you tell me how fast it is, you should probably tell me how to do it. Yes?
So X, the pointer points the value, not the key.
The pointer points to the node, but if I look at X points to dot key, I have the value, right? And now I know that the name that I'm looking for the one after is Romney, right? Well, now I have a pointer to, right, now in constant time I have got Romney, the name that I'm looking for the guy after. How do I find who is after them in logical order, in sorted order? Yes?
You keep track, you scan through the list, checking each node if its value is greater than the one you're looking at. Then if you're holding on to one, and then you keep track of
right.
that. And when when you encounter one that's larger.
Okay, so what he's saying here is that I know I'm looking for Romney. I'm looking for the guy that is bigger than Romney, but by the smallest amount, right? So I start at the beginning of the list. It says Skeena. Are you bigger than Romney? Well, you're after Romney in alphabetical order, which is really what we mean. So yes, Skeena is my successor now, temporarily. The next one is Abbott. Abbott's not after it. It's not going to change it. The next one is going to be Salamander. And Salamander is before Skeena, but after Romney, right? So it's the logical candidate. So by scanning through the whole list, I can do this. How much time does that take? So to find my successor, I claim is order N. Any questions about that? Yes?
That's logical successor, not physical successor.
Logical successor. That's how we defined it. We went back to, I gave you those definitions of what this thing was. If we went back here, logical successor and predecessor. These mean next and previous, I guess. It means that I want the next largest or smallest element. See that? Largest or smallest element. Okay? Any questions? Okay? What about finding the predecessor? How much time will it take to find the predecessor? The guy who's just before Romney. Right? Same logical thing. It's not really any different here on a singly linked, unsorted list. How do I find the minimum element? The one that's first in sorted order. Okay? How much time how can I find the minimum element in this linked list? Does anyone want a proposal? Yes? I could go through all the elements, and in order N time, that would be one way to do it. Okay? Any questions? Any other ideas? Yes?
It depends on, so if you record the minimum, if you keep track of minimum one every time you
So I could keep perhaps an extra pointer, okay, if you wish, pointing to the minimum element in the list and the maximum element in the list, okay? And then what would happen, okay, if I have a pointer to the min and the pointer to the max, then in constant time per query, I would be able to find the min or the max. Does everybody agree that if I have the pointer, then it would just take constant time? Now, what do I have to do to have that pointer? Okay, yes?
You would have to maintain it on every insert and delete.
I have to maintain it on an insert and a delete. So it is promising to have a pointer to min and max, right? But only if I can update it in constant, update it, okay, so that it doesn't add anything to the cost of insert or delete, which are the two structures that change my list. Does everybody agree with that? If I'm spending order, how much? Okay, I'm spending order one time here for my insert or delete. Does everybody see that? Can I figure out, after I've deleted, let's say, the min, how much time will it take to find the next biggest min? That would be order N. Does everybody see that? So if I hope to do this with a pointer here, okay, I am going to have to make, I could do that where I could make min take order 1 and max take order 1 if I was willing to make insert and delete order N time operations. Does everybody see the trade-off here? This is an important thing, and say if I don't see it, this is a good question. Yeah?
Wouldn't insert still be order 1? Because
What?
when comparing to the current min and max.
Okay, so insert, let's think about it. Insert would be order 1, right? Because now you're saying if I insert somebody who's before the min, I could update that, right? So we're agreeing that I could, if I wanted to, make min and max take order 1 time, keep insert at order 1 time. But then I would be doomed to making delete order N time, right? Because when I delete somebody, I need to find my min again. Okay? Any questions about it here? right? Isn't it? It's interesting. Something as dumb as searching in a linked list has become complicated. And the reason it's become complicated is there are trade-offs. Making something better makes something worse. Okay? Does everybody see that? And that to you, it's great if you can pull out a magic pointer that will get you where you want. That's perfectly fine, but you have to remember to spend the money, the time, to actually update that pointer. Any questions? Okay. Any other questions about this? Okay. So my preferred implementation here, it seems to me for this one, a logically consistent answer I can give is search in order n, insert in order 1, delete in order n, successor in order n, min in order 1, order 1. Okay? Or I guess I could do insert and delete in constant time at the cost of min and max, I believe, becoming order n. Any questions about that? Okay, yes?
So min and max is only one if you have a pointer to the min and max?
If I have a pointer to it, okay? If I think about it, if I had in my pocket the list of the name who was first in alphabetical order and the one who was last in alphabetical order, if anyone asked me who's in first in alphabetical order, how would I answer that? I'd read it off the card, right? Now what if they said, oh, that guy dropped the class. Now who's first in alphabetical order? Well, I no longer have it, I have no hope now, right? Okay, I have to scan through everybody to find that. Any questions? Okay, any questions about what these trade-offs are? That's interesting. Let's keep going. Now let's look at singly linked. Okay, do we want to look at singly linked sorted or doubly linked unsorted? Let's say doubly linked unsorted. Let's try this one, just for seeing it. What is going to be different if the links are if it's doubly linked lists, right? Now you're holding both partners here, right? Searching, how fast is searching going to be? What do I have to do to search for a given key? Still got to cruise through the whole list, order n. To insert somebody, I'm given an element. How do I insert it? Well, I've got to decide if I'm going to insert it at the beginning of the list. It's still going to be constant time, right? Now I'm going to have an extra pointer probably to update when I insert me, right? Because every element here is going to, the guy before me is going to have a predecessor as well as a successor. It's going to have to shake hands with me and stuff, but it's still going to be constant. If I am given a pointer to the element, how would I delete it? Okay, in a doubly linked list. Does everybody see? I now have a doubly linked list. I'm given an element here. How do I delete this one? In this case, I can do it in constant time without that fanciness, right? Because I can find the pointer of the guy before me. It will link to me. The guy after me, it should link back there. And now I'm gone, right? Any questions about that? So in constant time, I can be deleted. How do you find my successor or predecessor in logical order now that the linked list is doubled? Does that help me in any way? Doesn't help me at all. Still order n. Order n. And now, minimum and maximum. Well, again, if I want to get my insert and delete in constant time, I can't keep track of, I guess I can make, I can't make min and maximum happen in constant time because when I delete somebody, I'm going to have to go and search again for the next minimum, right? So basically, I'll do it at the time when I'm asked, and that takes order n time. Any questions? Okay. Yes?
Is there a formal way to prove that these trade-offs must happen?
Okay, is there a formal, what he's saying is, there seem to be trade-offs here. Is there a way to prove that there has to be trade-offs? That everything can't be fast? And the answer is yes, and the answer will come when I talk about a sorting lower bound. Okay, so file that one away. These trade-offs are not just Gee, the algorithm designers have been too stupid to find one that does everything right. Okay? There is actually a good reason as to why there must be a trade-off. And when we talk about the sorting lower bound, that will be clear. Any questions about that? Any questions about our unsorted lists? Let's now go back, trouble. Let's go back to the same thing. Let's now look at the sorted lists. Okay? If I have sorted lists, singly linked lists, how much time does it take, given my list, to search for a particular key? Okay, the list is sorted. What am I going to do? Yes? Still ON. Why is it still ON? Because it could be the last one. Does everybody see that even though it's sorted, which is usually a great thing for searching, if I have a sorted linked list and I'm looking for Zelda, Zelda is going to be at the end of the list. I can't get at that node without bopping through all the elements of my list. Does everybody see that? If it was an array, a sorted array, that would be great, right? Because a sorted array, I can look at the middle and do my binary search ideas, right? But it doesn't help me very much. Order n is still the time to search. Any questions here? What about inserting somebody into a linked list? If it's a sorted linked list, now I want to insert Skeena into the class. How much time will it take? Yes. O of n. Why is it O of n? Got to find where Skeena will go. Skeena will be nestled between two people. The one who is Skeena's predecessor and the one who is Skeena's successor. Does everybody see that? I have to find where in the list is that. So I'm going to bop through my list. Are you less than Skeena? Are you greater than Skeena? Are you greater than Skeena? Are you greater than Skeena? Someone will be greater than Skeena, I'm afraid. Okay? But the first person who says they're greater than Skeena in a sorted linked list is where I go. Does that make sense? So that is order n to do the insertion. What about a deletion? Okay, let's now think about deleting someone from a sorted linked list. Now I've got my sorted linked list. I am given this element. How much can I be deleted from it? How much time will it take to delete me from it? Okay? Yeah?
It'll take order n.
You say order n. Why is it order n?
You have the successor of it on the next, but to find its predecessor, you must start at the beginning of the list.
Okay, so the question is, if it's singly linked, I still need to find this predecessor, right? Now, if I'm going to do it the way I like to do it, I need that predecessor. And to find that guy, however, because it's singly linked, okay, I got to bop through the list. Can I use this guy's trick now to move the node? And the answer seems to be no. If I copy the guy at the beginning and land aardvark over Skeena, who just got deleted, right? It's no longer sorted. Does everybody see that? So in this case, in the singly linked list, my deletion is order n. Okay? Any questions? Now for my doubly linked list, let's think about my doubly linked list. What's that going to be for over here? If it was doubly linked list and I have a pointer to it, how much time is it going to take to delete it? Constant, because I can reach back to the guy that's holding me and the guy that's next to me, and I can bring their hands together, and I leave the dance. Is that right? Okay? So here is going to be a difference. Okay? Any questions about that? Okay? How do I find my successor in a sorted linked list? Okay, where is the successor to Skeena? Yeah. It'd be the next one in alphabetical order. Does everybody see that? So how much time will that take? Constant time. What about a predecessor? Where will we find the guy who is before Skeena, yeah? What? Order n, why? Again, it's singly linked. It's the guy whose hands are on my shoulder. And I can't get them except going back to the whole thing, right? So this, I claim, is order n. Any questions? What would it be in the doubly linked list? Order 1, constant time. Does everybody see that? What about the minimum and the maximum? Let's think about it. How do I find the minimum element in this sorted linked list? How much time will that take? Yes? Constant. How do I do it? It's the head, whoever the head is pointing to. That is then constant time. Does everybody agree with that? How do I find the maximum element in the linked list? Okay, let's say yeah. It could be I start from the head and go bopping to the end, and that would be order n, right? Or, yeah.
Can you just make a tail and then...
If I maintain a tail pointer, okay, then in fact I could answer it in constant time, right? Now, will I be able to maintain a tail pointer? Let's think about it. What operations change my data structure? It is insert and delete, right? Now, if I insert somebody at the end, they're going to go right after the tail. I think I know that, right? I can say, basically the element that if I'm putting this at the end, I'm going to have to update the tail, and tail goes to me. So I could certainly maintain my tail pointer on an insertion. What about a deletion? If I delete the guy from the tail, okay, well, I've got order n time on my insertion, right? Deletion. So if I delete somebody, I can make another pass through the list to find the last element in the tail and update it. Does everybody see it? The cost of making the second pass on the list is free, because what is n plus n?
Still order
N, okay? It's not the kind of arithmetic I teach my children, but n plus n is n in this class, because we're dealing with big O things, right? So a second pass through, so yes, if I maintain a tail pointer, I can in fact update that tail pointer, okay, in the course of doing my insertion or deletion. Yes?
Instead of going through again, every time you delete something, you can just check if the thing you're deleting is equal to the tail, and then at that point, you could update the tail.
So you're saying that instead of always going through and finding the new tail on every deletion, you could say only do that when I am actually deleting the tail, right? You're right. What you're saying is true, but I will say it is in some sense not interesting to me. Why? I am worrying about worst case, right? And if deleting the tail is what's going to be expensive, then the bad guys that are using my data structure are going to constantly delete the tail, right? I'm dealing with the worst case, right? So for that reason, what you're saying is true, and certainly when you program it that way, I think that's a smart thing to do. But big O-wise, it doesn't change anything. Any questions about that? Yes?
So during deletion, before you check every single element, you can check whether the element's the tail.
Well, okay, wait. If I have a pointer to the element, if I have a pointer to the tail, right, a tail pointer, and I have a pointer to x, the element being deleted, how do I tell if I'm deleting the tail? If x is equal to t. If they're pointing to the same thing, then I'm deleting the tail. Okay? Any questions? Okay? So bottom line, let's just think about the doubly linked sorted list now. Okay? To search in it is still going to be order n. I've still got to go through it. I still can't jump into the middle of my list. To insert somebody into a sorted list, I've got to still find where it goes. That's still going to be order n. To find my successor or predecessor, again, I've got hands on both of them, right? So in constant time, I've got that thing, right? My min and my max, well, min is certainly going to be constant because that's pointed to my head. If I can maintain my tail pointer, and in a doubly linked list, I believe I can maintain my tail pointer, right? The maximum element, when is the maximum element going to change? When I delete the previous max, right? But he's got a pointer to the guy that's right next to him. He's going to be the new king. Okay? So the answer is yes, I can update my tail pointer in constant time. Any questions about that? Yes?
Do you have the doubly sorted successor?
Doubly sorted predecessor and successor, I have order 1 and order 1.
Thank you.
I hope, okay? That's what I mean to have. Any questions? So does everybody, what should now be apparent that has to be feel in your kishkas, okay, is that these operations, how you do one depends upon how you do the other. How fast you can do them depends upon what other fields are you keeping track. It's okay to have a magic pointer pointing to what you want, provided you maintain that pointer when everything else changes. Okay? And so the cost of these things cannot be analyzed in isolation. It depends upon the implementation of this suite of operations. Any questions about that? Okay? Any other questions about how we maintain dictionaries with lists? Okay? Now, which of these is best? Let's think about it. Okay?
It depends.
You say it depends. That's normally a good answer. Now, in this context of this class, let's think if that's a completely true answer. The difference between doubly linked and singly linked is it just uses twice as much memory. We are not going to worry about that big O-wise, right? These things look strictly a little bit more powerful, right? This was a little bit more powerful than that. So this is not going to be a win, okay? We might as well make it doubly linked, right? And I think the same is probably true. They're not on the board, but if I went back and look at it, it didn't cost me anything. I'm pretty sure that I had more flexibility with the doubly linked one. I might as well have said this beats that one.
It was the same.
It was the same? If it was the same, which is better? Well, if it was a little easier for me to explain it and I didn't care about spending twice as much memory, that might be a better thing. Okay? If I care about the memory and they're the same, then I guess I would worry about the singly linked. Okay? Any questions? Okay, good. Any questions about this notion of trade-offs between data structure things? Okay? Good. So what I'd like to do is now talk about the king or queen of dictionary implementations, which is a binary search tree implementation. Okay? And what's good about binary search trees is that when you do them properly, they can give you a data structure that does pretty well on all 6 of these things. They offer about as good a trade-off between all of these things as you can get. Okay? So what is a binary search tree? First, let's worry about what a binary tree is. A binary tree is a tree is a rooted binary tree, is a rooted tree where we have a root. There are 2 pointers coming out of every node. Every node has at most 2 children. Okay? And further, the children can be identified as left children or right children. It's not that there are 2 children and you can't tell them apart. Okay? There is one that is strictly speaking the left child, one is strictly speaking the right child. Any questions about that? That is a rooted binary tree. Okay? And if that's so, then there are relationships in such a tree. Every node has a left child or has a left child that is nil. Every node has a right child or a right child that is nil. Every node has a parent or a parent that is nil. Who is the only node that has a parent that is nil? Root. Okay? Any questions about that? So that is the basic, I want to say physical structure of a tree, the linkage structure of a binary tree. Any questions? Now, what a binary search tree is, here's where we have this search thing here, okay, is a binary tree, meaning it is rooted. meaning it has left children and right children, where every node has a key in it. Okay? And further, the keys have a special property to it. That in a binary search tree, we have the property that for any node, all the nodes in its left subtree, meaning a descendants to the left, are less than it. Here, what's less than 7? 5 is less than 7 and 6 is less than 7. Right? What is greater than 7? Anything that's to the right of it has to be greater than 7. And 8 is there. If you look, for a binary search tree has the property that for every key node is labeled with a key, and everything in the left subtree is always less than the node of its root. Everything in its right subtree is greater than its root. Any questions about what the labeling property is? Any questions? Now, this labeling property is very interesting because it means that for any binary tree, there is exactly one way to label it with nodes, keys. Let's say I have a tree. I'm going to draw it. Here is to make it a little different. Ka-chunk, ka-chunk, ka-chunk. How can I make it weirder? Let's say I'm going to put a ka-chunk here. I now have a tree. You see what left and right is. I have 1, 2, 3, 4, 5, 6, 7. 7 numbers, things. Let's say the things I want to put in it are the numbers 1, 2, 3, 4, 5, 6, 7. My claim is this tree has exactly one way to be labeled with those numbers. Okay? What is the labeling of the root? Okay? If this is a binary search tree, if it's just a binary tree, you can paint it any color you want. Right? A binary tree. But for a binary search tree, the order of the keys matters. What is the label of the root going to be? 6. Why is it going to be 6?
Because there's 5 keys to the left of it.
Because everything that is on its left subtree has to be less than it. So what is it if you have 5 subtrees, keys, 1, 2, 3, 4, 5 nodes in its left subtree? That means that the node of this, value of this has to be, rank of it has to be 6th in sorted order. Right? That said, what is the value of this node going to be? 1. Why is that? How many elements are there that are in its left subtree that are? The answer is none. Anybody who is less than it is going to have to be in its left subtree. There is nobody there, so it is the least one. That has to be 1. Does everybody see it? I'm going to do this. What is the value of this node going to be? I heard the number 4. Why is it 4? It's got 2 guys to the left of it. Where are there 2 left guys that are remaining to the left of it? This guy is going to be 4. What is this node going to be? It's got to be 2 because the remaining guy that's in the space that's less than 4 is greater than 2. Does everybody see that the label ordering has to be like that? And what's left? This guy's got to be what? 5. And this guy's got to be 7. Okay? Does everybody see that? Yes.
It's in order, traversal is in order.
It's in order, traversal is in order when I cover it like that. And that's exactly what it means. The reason why the in-order traversal of the tree is basically going to give me the numbers 1, 2, 3, 4, 5, 6, 7 in order is because this is the one and only way to take that tree and label it so it is a binary search tree. Does everybody see this? There is the shape of the tree, which is a function maybe of just how it grows. But once you've got a tree of a particular shape and a set of keys, if it is going to be a binary search tree, it is going to have those labels in a very precise, only one order possible. Any questions about that? Yes?
Is this a unique way?
Is this the unique way? This is, if I am guaranteed to put down 7 keys, labeled 1 through 7, or A through, what is the 7th letter of the alphabet? B, G, okay? Then this is the way that it's got to be if it is that red tree. Note that there are lots of trees with 7 nodes, okay? I could make, here's another tree with 7 nodes in it, right? 1, 2, 3, 4, 5, 6, 7. What would the labels on that key tree have to be in order to if it's going to have the nodes 1 through 7? Yeah?
7 through 1 from top to bottom.
7 through 1?
I'm sorry, 1 through 7.
You can't just top node has to be the smallest one, right? Does everybody see that? There is one and only one way to label that tree with those 7 keys so that it is a binary search tree. Any questions about that? Okay? So we're separating the shape of the tree from its logical contents. Shape can vary, logical contents can't. Any questions? Good. Oops. Oops. No. Kabunk. Clear ink. So how are we going to implement our binary search tree? Well, again, this is plumbing now. This is now the shape of it. What is the physical topology? Well, I'm going to use a record where each node, I like to draw my binary search trees as looking like this. There is a left pointer. There is a right pointer. There is a key field. Here I call it item. Okay? And I could have an optional pointer, if I want, that would be the parent. Okay? For completeness, it is often good to be able to have a pointer to your parent, to get in touch with your parent. Okay? Any questions about that? Sometimes, to note though, that to get to a node like you, at one point or another, I had to know your parent. The only way to get access in this data structure is from the root on down, right? So if I've gotten a hold of you, it's because I got a hold of you through your parent, right? So it turns out to be sometimes optional whether you keep an explicit parent or not, okay? I kind of like to keep an explicit parent pointer. Why? Is it going to cost me anything in the big O notation? Instead of spending 2 pointers, I've got 3 pointers. Okay? I do have to do some work to maintain it when I insert it or delete it, but it does sometimes give you powers, right? If you had a node and it didn't know where it came by, let's say a node with amnesia, right? Oh my goodness, where I come from? If it's got a parent pointer, okay, it can go back to find its parent, right? If you don't have a parent pointer, you can't do that, right? I guess you can start at the root of the tree and search for you. Okay, that's I guess the way that you would find your parent. Any questions? Okay. So how would you do a search in a tree? My claim is that the way, because we have a binary search tree, we start at our root. The root has a value of, let's say, M. Let's say it's Monroe. Suppose you are looking for Romney. Where is Romney going to be? On the left side or the right side? Right side. That's right. Okay, that's good. I didn't notice that one. He would have been on the right side. Okay? But Romney, we would find Romney one step down. We can now look at the right side and go there. So what are we doing? We're comparing the element, okay, the key that we're looking for, to the data field of the root. If it's before it in alphabetical order, or if it's less than it, we search to the left. If it's greater, we search to the right. Notice that I'm doing this in a recursive way. Binary search trees are recursive things. What is a recursive thing? I think of it as something that when you make it smaller, it's still of that type. right? Okay? If you take a tree and you cut off one node, what do you still have? A tree, right? Not all things are like that. Okay, you have a person, you cut off the head. Is that person still a person? The answer is no, right? People are not recursive structures. But lists are, okay, and trees are, and stuff like this. And when that's true, you can exploit it to use recursive algorithms to deal with them. Any questions about that? Okay, good. Any questions about how you search in a binary search tree? What is the time it takes to search in a binary search tree? Okay, you have n things in a binary search tree. How much time does it take to search?
O of n.
Okay, I've heard log n, I've heard order n, but I haven't heard what I like to hear. Okay, what?
N log n?
N log n, if you think about it, is bigger than n. That would mean that it would take more time than it takes for the entire things in the tree. That would be really disastrous. Okay? So that's not right. Okay? Yeah?
It depends.
It depends is a good answer. But it depends upon what?
The shape of the tree, maybe?
The shape of the tree or the height of the tree. That is the kind of thing that I would say. If I'm given a binary tree on n nodes, I would like to say that having just said, unless you tell me something else about that binary tree, okay, the time it is going to take is proportional to the height of the tree, right? Isn't that log n is what he's saying? Well, it depends what we're dealing with. Remember at one point I told you ka-chunk, 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 ka-chunk was a tree. So if I have a very badly shaped tree, I do not have a guarantee that it is log n, right? This is a sign that I don't want badly shaped trees, and that I'm going to later try to figure out ways to avoid them, okay? But you're telling me, you said order n. In the worst case, the height of the tree is going to be order n, so you're not really precise in saying order n. But the way that I would like to say it is order the height of the tree, okay, is right. The worst case time is every time in constant time I move down one level, right? And I can only move down as many levels as the height of the tree before I clang off a nil pointer. Okay? Any questions about that? Does everybody agree that it is order h, the height of the tree? Good. Now, how do I find the minimum element or the maximum element in a binary search tree? Where is the minimum element? Okay? The minimum element is, if we think about it from the root, if it's going to be less than the root, where is it going to have to be? On the left side. If it is less than that, where is it going to be? On the left side. Does everybody agree with that? So going down leftmost pointers until I hit nil, this is the minimum element. And going down right elements until I hit nil, that is going to be the maximum element. How many people see that? How many people don't see it? Any questions about that? So how much time will it take to find the minimum element in a binary search tree or a maximum element? Yes?
O of h.
Order h, time proportional to the height. Any questions about that? Okay. Again, if you look at my code, I think I give you a little code, but I mean, this should now not be so hard to see. What am I going to do? To find the minimum. Okay? In this case, it's find minimum. You could do it recursively, actually, because find min for me is my right. Do I have a left child? If so, find min of the left child and report that. But here I chose to do it with an iterative thing, right? So long as the left pointer is not nil, keep looping until I find one where the left pointer is nil. If so, then I am the min. Any questions about that? How many people here see how this could be done recursively? Just to see where people's heads are. How many people are confused about how you do it recursively? Any questions? Which is better, doing it iteratively or recursively?
Doesn't matter.
I hear recursively. Why do you think it's recursively? Well, professors seem to like things recursively. Okay? What would the time of the recursive thing be? In constant time, I'm going to look at my right-left pointer. Am I there? If so, call myself recursively on that node, right? It's going to take constant time, and I move down one level, right? This takes constant time, and I move down one level, right? Both of them are going to be order height, proportional to the height. In a big O sense, they are the same thing. Any questions about that? Yes? Okay, any questions about that? Okay? Yes?
When you say order height, isn't that log n?
Well, is it order height? It depends upon how I do my... You're saying, isn't the height of this tree log n? It's only log n if I can make it log n. Okay? Meaning that if I can do something so that whenever I do an insertion or a deletion, it never gets out of whack, then it will be log n. Right? But that is a somewhat complicated thing to do. Okay? And if we were, depending upon how we're going to do my insertions or deletions, I may not be able to force the shape of my tree to be like that. Okay?
If it was a test, then you said log n or height, you would be fine either way, or...
Well, you're saying, what would be the answer be on a test?
Yeah.
What the right answer would be if the question said, how much time does it take to search in a balanced binary search tree? Then that would be order log n. How much time does it take to search in a binary search tree where you have no other guarantees? It just came down the street, you don't know where it came from? Okay? That could be order n. Okay? Any questions about that? Okay? Do people see what it is? Why this would be? When we get to insertion or deletion, this is where the critical issue is going to be. Any questions? What about predecessor and successor? I'd like to avoid this insert and delete stuff because, it sounds complicated. How do I find a predecessor or successor? Okay? Let's think I was starting to look at this thing. Where would, if I was starting at the root, where would the one who is logically just before the root going to be? Okay? Yeah?
Is the maximum or the less entry?
Does everybody see that the guy that's going to appear before me, right before me in sorted order, if it's before me, it's got to be on the left. Okay? Which one is it going to be? It's got to be the biggest one on the left side, right? Ka-chunk, 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 that's going to be the max. Does everybody see that? So the way to find me, if I was the root to find me, would be my predecessor is the max of the left subchild, right? My successor is going to be who? Go to the min on my right child. Does everybody see that? That's going to be this guy over here. Okay? So if I have a node where it turns out an internal node in a tree, not just the root. For the root, I think that's pretty obvious. For any node in the tree, if it's got the appropriate child to the left or the right, okay, the same principle holds. Okay? The way I look at it is, every node in a binary search tree is indeed defined by a key, but it's also sort of, another way to think of it, it defines a subrange. The root defines, I am the king of all my descendants, okay, meaning that the descendants go from anywhere to the left, all the way to the beginning, to all the way to the end. When I move down this node, what does it mean? Everybody from this node, as far as it's concerned, is greater than the root, right? It could have any value here so long as it's greater than the root, right? And if I move down over here to the left, This node here is going to have the value that it's got to be greater than this thing and less than this thing. So every node is going to define an interval in key space, if you wish. Okay? Telling you what values that node could possibly have based on where it is in the tree. Do people see what I mean by this? I don't know how many people may not see this one. Okay? But basically the reason why what I just said holds for any node, you go to the left and pick the max, or go to the right and pick the min, is true because everything I said for the root is true for any other node in here. Okay? Because they both define a range of space around what's bigger than it and what's less than it. A sort of a continuous range of space. Any questions here? So how much time should it take to find the predecessor? Okay, using this argument. If I want to find what my predecessor is, okay, how would I do it? What is the predecessor of this? How much time will it take to find the predecessor of this node? What do I have to do? Yeah?
You say it's big O of h over 2?
Well, what am I going to do? I'm going to go to the appropriate side and find the min or the max. You say, is it O of h over 2? Notice that when I move down that one level, did I shrink the height by 2? Or did I shrink the height by an additive 1? If it's O of h over 2, if you're coming up with an answer like that, you're saying I cut the height in half, right? It's like I chopped it at the midsection, right? The truth is I shortened it by 1, right? Because that 1 is that pointer I traversed, right? So it is really now one step, and then I have O of h minus 1, right? Yeah?
Can't you argue that you're cutting off half the tree because while there's the left or the right, you're...
Well, I'm cutting off half the potential number of nodes, which is a function of n, the number of nodes, right? But it also depends upon what I even know what half the tree means. If my tree looked like this, then moving down here, I didn't cut off half the number of nodes, did I? I cut off one node, right? So without making statements about what the shape of the tree is, I don't see how you can make such a statement, right? Any questions about that? The other thing that I cringe a little bit with what you were saying was you said something like order h over 2. What is order h over 2? Yeah? Order h, dividing it by 2, or 10, or 100, or 1,000,000 doesn't change it as far as I'm concerned, right? It's still order h, okay? Adding 1, or 2, or 3, or subtracting 1, or 2, or 3, or 1,000,000 doesn't change it. It's still order h, okay? Any questions about that? Okay? Any questions? So it should be clear that if I have a node in the internal thing, the time it will take to find the predecessor or successor is order h. Okay? Any questions? The real question that's a little tricky is, what about a leaf node? Okay? Let's come back clear ink. What would be, if I take a look at my tree, what is the predecessor of this red node? Okay? Where can it be? I would like it to be, if I had a left subchild, I know where my predecessor is because it's got to be one of my descendants to the left. This node is a leaf. It does not have a left subchild, right? Does that mean it doesn't have a predecessor? No, it's going to have somebody in alphabetical order. This could be Shapiro, okay? There's going to be somebody who is going to be before it in alphabetical order, right? Which one is it? Okay? Yeah? Its parent. The answer is not necessarily its parent. Okay, is it possible that how can we argue that the parent is not necessarily the predecessor? Yeah?
What if it were a left leaf?
What if it was a left leaf? Does everybody see this thing? That for this node, its parent was it in fact bigger than it, right? So it couldn't be a predecessor. So it's not quite the parent, okay? It turns out to be, it's a little tricky, but if you play with the tree a little bit and you think about it, okay, clearing, ka-chunk. The basic argument turns out to be the following. If I look for a successor to a leaf node, okay, who is its successor going to be? Let's say the predecessor. Let's say I'm looking at this node. I want to find who its predecessor is. If I go up to its parent in this case is a left parent. That means that I am less than my parent, right? Does everybody see that? So my parent can't be my predecessor. Grandparent can't be my predecessor because it's always going left pointers. It turns out my first relative, my first ancestor, who there is a right turn, that is going to be my predecessor. Does everybody kind of get that idea? This requires thinking about a little bit. Okay? We want it to be our parent. It can't be our parent because it depends upon the direction of the parenthood. Right? In fact, what it really means, if we go up to enough ancestors until we see the turning point, right? What happens if we have a node that never has a right ancestor?
You mean a left ancestor?
Well, in this case, a left ancestor. Let's say we call that a left ancestor. Let's say we have a node that never has a left ancestor. What property is that node? Yeah? The minimum, right? Does everybody see that? What's the predecessor of the minimum? There is none, right? So it should be clear that by doing some kind of thing of walking back up through ancestors, okay, I should be able to tell whether I can test. If I have the node and I have the pointer, am I a left child or a right child of it? Right? So how much time, assuming I have parent pointers, how much time will it take to find my predecessor or successor in this means? Yeah?
Still order H.
Still order H, time proportional to the height of the tree. Does everybody agree with it? Here's where having the parent pointers are useful. Okay, and so we'll assume we got parent pointers. Any questions about that? All of these are still order H time. Any questions? Okay, now let's get to the tree restructuring parts. How do we go about inserting something into a tree? Okay, suppose, let's say, that I have this tree. Let's say that that's my complete tree. And I decide I want to insert an element 6.5. Okay, does everybody see this tree? I want to insert a new element 6.5. Where is it that 6.5 must go if it's a binary search tree? Okay? I start at the root. Where must element 6.5 go? Is it on the left side or the right side? But it looks like there's a lot of room on the left side. Doesn't matter, right? If I'm going to keep it as a binary search tree, there is one and only one place where it can go. It can go to the right. Now where can it go? To the left or the right of 3? Right. To the left or the right of 7? Left. To the left of the right of 6? Right, that's a nil pointer, right? Now I can insert it in there, okay? And in time proportional to the height of the tree, I can find where is that one place and only one place where it can go. Does everybody see that? Okay? So by doing insertion this way, it is going to take order H time to do that, where H is the height of the tree. Any questions about that? Yes? What if I have two numbers with the same value? Then I'm in trouble. And so what I'm going to do is not allow myself to have two numbers of the same value. Okay? Just like Are there any two students in this class with the same university ID number? No. Why is that? Because the gods that run the university did not allow it, right? Are there two people in here who have the same name? Quite possibly. I couldn't control that, right? So these systems break down if I have keys that are identical. So how can I deal with keys that are identical? One is to forbid them. That's a good way, right? But what if in fact they are going to be inserted? What would be a way I could do that? Any ideas? Yeah?
Each node is a list.
Maybe I will make each node a list. I will add to my record for my node a linked list that says, maybe my next field. And so for all people who happen to be named, John Smith, they will all be, sort of stuck. Once you look at me, you say, oh, this guy is where I'm going. There already is a John Smith. I will be put in John Smith's list, right? So everybody see how that way I could actually store the guy in my tree, but not have to worry about equal keys. Yeah.
Another solution we could use is to amend the definition of the tree so that the left subrange is for everything that's less than the current value and everything.
Okay, there are ways that there may be other ways to define it, but now these things start to get more slippery. Okay, and you have to be careful. You make sure you get everything right here. And if you think about it, how much time will it take to search in a tree like this? One of your trees. Let's say I want to try to find a particular schema. If there are up to n nodes in this tree, each of which are different schemas, my clones, okay, to find me, how much is it going to take to find me? You've got to look at all the nodes in the tree, right? And so suddenly weird things happen when you allow equality, okay? So we're not going to allow equality in here, okay? Any questions about that? Okay? But does everybody see, and this is the important thing, that the time to do this was time proportional to the height of the tree? Any questions about that? Now, this insertion method, you guys were complaining, are the tree going to be of log height? Is the tree going to be of log height if I do insertion this way? Not necessarily. What happens if I'm starting to insert people into the class, and the first person to come into the class is named Aardvark, and the second person who wants to join happens to be named Bill? They're going to go there, right? And the third person that's getting inserted in the class happens to be Kathy, followed by David, followed by Eddie. Does everybody see this? If I'm doing insertion this way, my tree might not be nice and balanced. It depends on, if it's balanced, it depends upon the order of what is being asked of me to insert. I do not control the order in which insertions are happening. Okay? Any questions about that? If people see that, that's an important point here. Okay? Any questions about it? So if I do this, my insertion takes time, order H, but I did not constrain you to make sure that the tree is going to be balanced. Okay? I'm at the mercy of the order of insertions. Any questions? Good. Let's look at one last operation, and then I promise I will let you go for the day. But this one is a complicated operation. Okay? This is deletion. How do I delete a node from a tree? Okay? I'm given a pointer to the node for my deletion, so I don't have to find it, so that's good. Okay? But once I delete it, okay, how can I delete it? It turns out to be tricky because trees have two left children and right children. Let me kind of make this clear with this picture. Look at this particular set of trees. If I want to delete node 3, this node, what do I have to do to delete it? Okay? If I want to delete that node, what is the way that I delete it so that the tree will not know that it knows that it doesn't exist? What must I do? Yes?
Go to the parent, nil out the left child.
Nil out the parent pointer. Does everybody see that? I nil that guy out. I've got this situation. Okay? Any questions? So if I'm deleting a leaf, that is fine. That takes constant time. That's not a big deal, right? Clear ink. What if I am deleting a node that has one child to it? This node, okay? What I could do is, okay, if I'm deleting 6, I could take, it's got one subtree, a left subtree. There is a parent pointer. After I'm gone, the thing that is my child has to be pointed into the tree. I've got one pointer to do it. By just wiring my subtree back to this one. That will preserve the tree order. Okay, you can see it doesn't matter if it's a left child or a right child. If I have one descendant, okay, and you want to remove me, then you simply overwrite me with that's sort of the similar trick that this guy was doing, okay? And I can be made to go away. Here I deleted 6 by overwriting it with 5. The problem comes when, okay, what is the problem? The problem comes, what if I delete a node with the property that it's got 2 children, right? My parent, after I am deleted, has one spare pointer to give. But there are 2 different subchildren here, right? Does everybody see that? And that presents seemingly a problem. Okay? So this is the hard case. The other cases were constant time. Deleting an internal node with 2 children is trickier. How do you do it? Let me see if I can say this in a minute. Okay? Well, what I'm really going to do here is relabel the node with its successor. Okay? If I have an internal node, its successor is going to be a leaf node. So I'm going to relabel me with my successor, and then delete the successor, which is an easy case. Does everybody see that? You don't see it now, but if you thought about it, you would see it. And the time that takes is going to be dominated by the time it takes to find the successor, which is order H. Any questions? Think about it. And next class, we're going to polish off discussions of trees and then talk about other good dictionaries. Thank you for your attention. Talk then.